Section 3.7 is about inverse functions, and this really follows most closely off of section 3.4 on the composition of functions. Inverse functions have a close relationship with composites, or composite functions. So first I want to start off with an example that'll relate this to something somewhat familiar. C equals 5/9 F minus 32. Gives the temperature in Celsius, so Celsius temp, in terms of the Fahrenheit temp. So degrees Fahrenheit, if you know what the temperature is in Fahrenheit, you can use this formula to find the temperature in the Celsius scale, the centigrade scale. This is an inverse function relationship, and I want to show you how we can use this formula to get a new formula that will give me the Fahrenheit temperature if I know what the Celsius is. So it's the reverse formula of this. What I'll do is, what I want to do is solve for F. So the first thing I'm going to do is multiply on both sides by 9/5. The reason is that 5/9 times 9/5, that goes away, that's 1. So I have 9/5 C equals F minus 32, and then one more step, plus 32 on both sides. 9/5 C plus 32 equals F, or a little bit better way, more readable, is to say F equals 9/5 C plus 32. So these two have this special relationship that we're looking at in this section. These two are inverse functions of each other. This one gives the Celsius temperature. This one gives the Fahrenheit temperature. They're really the same relationship. It's just, if I think of them as functions, they're inverses. So I want to point out some notation for inverse functions that'll help us write them down without too much writing. And so the notation looks like this. The inverse of f of x, a given function, is written f inverse of x. So this is a new notation. I know we've used the -1 exponent before. It means reciprocal when it's applied to a number or to a variable or even to a variable expression. It's not here. This is the inverse function, which is more like the reverse process of whatever a function does, the inverse function undoes that. And I do want to make an important note about that f inverse of x is not f to the -1. It's not 1 over f of x. Very rarely that might be a coincidence, but that's not what the notation means. It means the reverse function, or the reverse process. So I have a little definition that has, first of all, f inverse of x is the inverse of f of x. Well, that's what I use the notation for, but what it means is if two things are true. First of all, f is 1 to 1, and that's not what we're going to emphasize in this particular lecture, but f has to be a 1 to 1 function for this to work. The important thing for us is when f of a is equal to b, we have f inverse of b equals a. And that is the reality or the important thing about what inverse functions are. So I have this input a to the function f. F of a gives me this number b. Then if I apply the inverse function, f inverse, to that b, it brings me back to the a value from which it came. I've got a picture. In a little bit, we'll look at a picture that kind of demonstrates this relationship, but it's the reverse process. So whatever an input gives me as an output, the inverse function takes that output and gives me back the original input. It undoes the function. I have a test here that you can use to decide if two functions are inverses, or if you're finding an inverse, you can use this to check yourself. Testing if two functions are inverses of each other. And it works like this. If you do f of f inverse of x, so this is the composite function. I'm not using the little circle notation here, but it is plugging a function into another function. And what happens is, whatever the inverse function does to this, f does the reverse, and we get right back to whatever that input is. And it works the other way. If I do f inverse of f of x, that also brings me back to x. So the functions will undo each other, and we'll see an example of this presently. So here's an example of not finding an inverse, but testing to see if we actually have the inverse. In this example, f of x is equal to 1 over x plus 2, and g of x is equal to 1 over x minus 2. The question here is g of x equal to f inverse of x? In other words, are these two functions inverses? And I'm going to check that by looking at f of g of x, plugging one function into the other, and we'll see what that means for them to cancel each other. I like to do it one at a time. G of x is 1 over x minus 2. So I'm plugging in the formula for g of x. Now I'm going to plug that expression in for x in my f function. 1 over x minus 2 plus 2. See, I've taken this expression and substituted for the variable in the f formula. 1 over g of x plus 2. And now if I simplify this, this is 1 over x minus 2 plus 2. So these parentheses aren't actually grouping anything that needs to be distributed. I can just drop them. But minus 2 plus 2, those cancel, leaving 1 over x. So the reciprocal of x is one way to look at this. Another way to look at it is I'm dividing by a fraction, so I need to multiply by the reciprocal, as in 1 times x over 1. Either way, that gives me just x. And so what this means is that when I plugged the g function into the f function, whatever I plug in there, whatever x value I have, I'm going to get that same value out again. And that is the check. That we're checking if g is actually the inverse. And we're not done yet, though. The other thing I need to check is to make sure that g of f of x is also just equal to x. Whatever I put in there is exactly what I get out. Now I'm going to do it like I did before by plugging in the formula for the inside function, 1 over x plus 2. And there's f of x. Now g of that is 1 over 1 over x plus 2 minus 2. So I'm plugging in this whole rational expression or formula for f in place of x in the g function. This is the composite function. What happens here, similar to what we did before, the reciprocal of the reciprocal is just whatever that thing is, x plus 2 in this case, minus 2. And that is equal to x. So check in the other direction too. So f of g of x is x, and g of f of x is also x. So the answer to the question is yes, g of x is the inverse function for this given f of x. Sometimes this is called verifying that two functions are inverses of each other. I want to mention briefly, we're not going to find many of these, but looking at the domain and range of inverses does more than just, well, there's more to it than just finding the domain and range. Looking at that relationship can help us understand what inverses are doing. And I have a picture where I'm going to have a couple globular regions here. Not really supposed to have any shape in particular, but this one represents the domain of f, and this one represents the range of f. So domain and range. And if I have a point x in the domain, then somewhere in the range there's a point f of x. Or y, if you want to call it that, but we've already got a name based on, we have a function name and we have a variable or a value in the domain, f of x. The function can be thought of as a map or a way of corresponding this point to this point. And that's a picture of what function means in terms of domain and range. Now, to connect this to inverse, the inverse function should take that point, f of x or y, whatever you want to call it, and bring it back to the very same place that it came from. It's the reverse of this function. So whatever this function brings this over to, the inverse function brings it back to where it started. And the reason I call this domain and range is this is the domain of f inverse, and this is the range of f inverse. In summary, I'm going to write this whole relationship and picture idea in symbols. The domain of f inverse, the domain of the inverse function, is equal to the range of the original function. And the range of the inverse function is equal to the domain of the original function. So if you're asked to identify the domain and range of an inverse function, you can do that with the range and domain of the original function. Sometimes it's easier to find one function's domain or range than another's, so you want to go with the easy one, but it's these identities that help us do it the easy way, if possible. All right, so the last topic for the section is how to find the inverse function. And I've got a little outline, 4-step process. I think the book had a 3-step process, but I think it's easier to break it into 4 steps. So I'm going to outline those steps and then use them on a couple examples. Finding the inverse. So we have to start with something. They have to give us a function and then find the inverse. It can't always be done because sometimes what we find will not really be a function. For our problems, it will. So the first step is to replace the notation f of x with y. And I'm not really talking about doing any math here. I'm talking about writing y equals whatever the formula is. Instead of having that, it's a symbol, f of x, that's made of 4 separate symbols. So y is a single symbol that we're going to use to make things easier to write. The second step is to interchange x and y. What that means is anywhere there's an x, I'm going to make it a y, and anywhere there's a y, I'm going to make it an x. Interchange. Swap or switch. The third step is the actual algebra step, where we actually do the work of finding this formula. Solve for y. The formula that we get from step 2, we're going to solve that for the y variable. And then finally, replace y with f inverse of x. And again, I mean just the symbol. You're going to have an equation here with the variable y. You want to change that y into this symbol that represents the inverse function of the given function f. So I don't have room to do all this for the example, so use these steps. I'm about to use these steps, and I'm just going to label them with their numbers 1, 2, 3, and 4. In this example, we're going to find the inverse of f of x equal to 2x minus 6. So my first step is to replace f of x with y. All I mean is to write it as y equals 2x minus 6. I'm writing the formula down with a variable instead of a big old compound symbol. Second, I'm going to interchange the x and y variables to get x equals 2y minus 6. Not really math, I'm just swapping. Here's the step where I'm going to solve for y. So I'm just going to build it from this equation. I've got it right here. I'm going to do plus 6 on both sides. It gives me x plus 6 equals 2y. And then we're solving for y here. Divide by 2 to get, well, that's it. I've solved for y. Y x plus 6 over 2 is the expression. And it looks backwards. You could write it the other way. In fact, in step 4, I'm going to replace that y with f inverse of x. But the other side is the formula, x plus 6 over 2. And that's the inverse function. So my fourth step actually gives me the answer. Now there's another way to write this one. You can write this as 1/2 x plus 3. Just dividing the terms of the numerator by 2. This way, f inverse of x equals 1/2 x plus 3. This way is kind of useful because you can see that it's a linear equation. Y equals mx plus b. So a slope of 1/2 and a y-intercept of 3. But this is fine, as far as I'm concerned. This is a good way to look at it. Unfortunately, with multiple choice type questions and quizzes and exams, you have to find the one that matches. So if you don't see your result, try to simplify it, express it in a different way, and see if that appears in the answer choices. I think this is a great answer, but this is also the same thing. Okay, I've got another example. It's a little bit bigger, just in terms of the function formula. Instead of being a linear function, this is going to be for a rational function. So let's take a look at this example, find f inverse for f of x equal to 2x over x minus 3. Like I said, rational function. A little more complicated, and it's going to take a couple more steps, but as far as the steps of finding the inverse, it's just 1, 2, 3, 4. We'll go through those same 4 steps. I'm going to write y equals 2x over x minus 3. Just replacing the function notation with the variable y. Then, interchanging x and y variables. That means wherever there's a y, I put an x, and wherever there's an x, I put a y. I want to change all those x's. Well, there's 2 of them here. I want to change both of them to y's. And then the third step is where I solve this equation for y. It's a little bit, it might be a little bit unfamiliar to you. We're trying to isolate y, so we can have y equals the stuff. There's 2 y's though. Well, it's the same variable, but I have to very carefully take apart this expression so I can rearrange it to get y isolated. There's only one y. I mean, it shows up twice, but it's the same variable. What I'm going to do first is multiply both sides by y minus 3. So over here I get x times y minus 3. And over here, well, it's 2y divided by y minus 3 times y minus 3. Those cancel. All that's left is the 2y. That's why I did it. Multiplying by the denominator on both sides. And it's not even a rational expression or rational equation anymore. I guess that's kind of linear. We still have to solve for y though. And the next thing would be to distribute the x. Xy minus 3x equals 2y. And then I need to get all the y variable on one side of the equation. I'm going to do it like this. I'm going to subtract 2y from both sides to get, let's see, xy minus 3x minus 2y equals, it's 0. But I want to get the stuff that doesn't have y over there, so plus 3x on both sides. And that's xy minus 2y equals 3x. You could do both of these steps in a single step. You just have to be a little organized with what you're doing. Maybe keep the y terms lined up and then do the plus 3x terms lined up. The result should be the same. But now, since all the y's are on this side, I can factor that y out, leave the remainder x minus 2. So factor out that common factor of y. And then finally divide by x minus 2 on both sides, and I get y equals 3x over x minus 2. And that's it, other than what I called the step 4 was to put the inverse function notation, f inverse of x is equal to 3x over x minus 2. And that's the inverse function that we were looking for. You can check them. So this was my original function, f of x. This is my inverse function, f inverse of x. We could do f of f inverse of x, and the result would come out to just x. You do it in the reverse order, and the same thing would come out to just x. So these are actually inverses. I'm not going to check this one, but feel free to if you want some practice.